In this part, we're finally going to get to some actual gameplay, namely the trash section of the game. So we're going to start off with this section of code that I actually showed before in part 1 overview, but I thought that it had been loading sprite data for the opening cutscene, but it turns out that's not the case. I was right about the overall control of going to main screen and then either going to the cutscene or the settings screen, and generally about that, but for this particular section, it is actually loading the trash data. If we look right here, so we've got several MVN instructions which are going to be used for moving chunks of memory. And so if we take a look at this first one, the start address is B38, and then the value in the accumulator is going to be 2C, which is the amount of bytes to be moved, or more specifically, one less the amount of bytes to be moved. And if we add 2C to B38, then we'll get B64, which is one before the next, the beginning of the next block of memory to be written to. So this move instruction right here is going to copy over B38 to B64. And so what do we get if we look at those values? Well, it just so happens that that corresponds to the first piece of trash. If we go ahead and get into game, you can see I've figured out a good amount of the values here, what they represent for the piece of trash. So it's going to initialize them here. There we go. You can see we've got a bunch of values now. So I've figured out most of them, or most of the other ones that aren't labeled are either constants between the pieces of trash, or they just always remain the 0 and don't appear to be used. But so this is the first piece of trash. You can see this this first value here is the rotation direction. If I actually let this run a little bit, so I can isolate the piece of trash. The trash value is 19, so that means that we're looking here at this piece of paper. That is the first piece of trash. And so now if we note the rotation direction, it seems it's going that way, sort of counterclockwise. And this value actually is, well, if you think about value 33 written in binary as 2 1s in it, the one for like the 32 place and the one for the 1s place. So some of these values don't actually use the whole byte. It's just, some of them are just Boolean values. So that 1 in the 32's place is the relevant bit here, where if we change this to just 1, so just flipping that 1 bit, that's going to flip the rotation direction. So now you can see it just flipped direction, and now it's going clockwise. So next we have the position for X and Y, and it works with, I'm calling this subpixel. I don't know if that's the most accurate term, but basically it takes the speed value that's down here. We've got X and Y speed, and it adds that to the subpixel, and when that goes over 256, the maximum, or when it goes over 255, the maximum value a byte can hold, it moves over a pixel. So actually it'll be easier to explain once it rebounds from the other side, but you can see as it moves to the left, X position is going down, and because this particular piece of trash has no Y speed, it's just the X position is changing, so that Y position is going to remain constant at 59. And so you can see the X speed has actually changed to 96. That's because of a sort of strange way that the game does this calculation. So while it's traveling in the positive direction right now, as X position is increasing, if we go frame by frame, you can see we've got an X subpixel of 0, and then if we add a frame, it goes up to 96, and then 192, and then if we add 192, if we add 96 to 192, that'll be over 256, so X position will increase by 1, so we should see X position go up to 9, and we do, and the remainder is 32. So that's sort of the standard way that it works. But for whatever reason, when going in the opposite direction, the way they have it designed, it changes the X speed to 256 minus the X speed. So that's why initially it was 160. And then it adds 160 to the subpixel each time and subtracts 1 from the X position every time that it doesn't overflow. So that's mathematically equivalent to just subtracting 96 from the subpixel and subtracting 1 from the X position when that underflows, but for whatever reason they've chosen to do it this way, so the speed does remain constant, but the variable that they're using for speed is dependent on the direction. And X direction here is going to be 0 or 255, depending on the direction. So if it's traveling to the right, and we change that to 255, we should see it turn around and go the other way. And you'll see this time it did actually increase in speed because I didn't change the speed variable, so now it's going at an effective speed of 160 to the left. So what that translates to is all of the speed values that the trash can be are all in multiples of 16, and of course the value for whether it increases a pixel is 256, also known as 16 groups of 16. So if it's going at a speed of 96, that's 6 times 16. So that means that every 16 frames it'll go 6 pixels, or every 8 frames it'll go 3 pixels. So that's how the speed works. The Y position works the same way. We would just need to look at a piece of trash that actually has Y speed, or we could even just change this piece of trash so it has some Y speed. So now it'll start moving downwards at the same speed, so it should be moving at a 45-degree angle there. Now there are several variables here that all have the same value. These two that are labeled animation iteration, you can see it's the same value as this one down here. I don't know the reason for the multiple different ones, but that's as it steps through the animation. So you can see it's at one particular sprite, and then eventually when it changes to 112, see the next frame or a couple of frames after, it'll change to a different picture and it'll stay there for a while. 113 it'll be change it to another picture, so that's just the animation that it's stepping through. And I believe it's this, the animation frame, this is actually like the amount that it's adding, so it's stepping through from 0 to 7 as it goes, and then that's added to another value to get sort of the index for what picture to actually load, and that's what ends up in here. Enable number display. That's mostly used for when you actually shoot a piece of trash. Like if you shoot a piece of trash that's the wrong number, so like this one is not the correct answer, but if we shoot it, when it respawns, it won't have a number displayed on it. So you can see this. This is another one that just uses 1 bit. So it's just flipping that 1 bit to a 0. And now this bottle over here, you can see that's what we're looking at now for trash piece 1, and it doesn't have that number display, but if we just manually re-enable that, it will come back up and display trash value. Coloring has to do with the different type of trash piece, like whether it's a comb or a bottle or a can or whatnot. That is actually determined by a separate value, but then this coloring value is also changed in order to just make the color look accurate. If we change it to a different value, you can see the color will change. It'll be all off. So it'll be the same type, but it won't be the correct light color palette. So if we wanted to change this completely to another piece of trash, we can actually tell by, if we just load another piece of trash. I don't have the labels here, but it is this value, so that one actually is the same one. And so is that one. I believe there's, I know it can be 8 or 12 as well. There we go, so this one's 12. So this is the 7, which looks like it's the cone thing here. So that one has a coloring value of 12, and if we go back to piece 1, we can see the other value in question is down here, trash type, which I think is it's like the starting value of the of this sprite to use. So that's got a value of 124 currently for the bottle, a coloring value of 10. But if we go to P6, it's got a different value. So if I wanted to turn this into a bottle, we'd have to change this to 124, but then it would change, but now it's got that color palette that looks wrong, so we have to also change the coloring value. So now it's completely just a bottle and indistinguishable from this other piece. So those are the two relevant values for trash type are the coloring and the trash type value. And so the only other thing here is really the correct piece. So this is how the game keeps track of which piece of trash is actually the right answer. So in this case, looking at the 2 here is obviously not the right answer. And this is another variable that just uses one of the bits. It's actually the second bit here. So the correct answer here being 7. And so if we switch over to this last piece, you can see the value of this piece of trash is 7. And so this also has 64, meaning that just one of the bits is flipped. So that means we could actually just trick the game into doing the math wrong. So if we go back to this first piece here, the 2, and just change the correct piece, flip that bit. So now both 7 and 2 are valid answers. So if we shoot 2, it's going to say correct. It still says 5 plus 2 is 7 because the graphics are handled separately, but there we go. So that's basically all of the trash values. There are still a couple other topics in trash to cover. For example, the rebounding, the bouncing effect as the trash pieces go off screen and then bounce back. So the piece of trash that we're watching is now this can at 23. So the first place it's going to rebound will be the top of the screen. So if we watch Y position as it goes off, it'll go below 0, and that's what this Y overflow value is for. So that's when it's below 0, then Y overflow is going to be 255, and then if it were to go over 255, then Y overflow would be 1. So that happens in the X direction, but that doesn't actually happen on the Y direction because the field is not that large. But you'll see it actually jump in value a little bit when it hits the top of the screen. So you can see it going down slowly, and then it just jumps from about 10 pixels, from 230 something to 240 something. And so that's the case on all 4 sides of the playfield. And I've created this graphic here to visualize it. So you can see that outermost layer is the bounce and clear detection. So that's once the piece of trash has reached that value, that's when the game detects that it's off the playfield, and it updates the value down to something within the trash area. So it just jumps it up to the border of the trash area. And it'll do so just on the y-axis. So you can see if it's at, on the way it's done in this chart, that's positive. So positive y values on this chart are going to be a y overflow of 255. So if it's 25 below that, then it'll jump it back up to 14. And then it'll continue on its way with the reverse direction. And so the inner square is the range of the cursor movement. There's variables for the left, right, top, and bottom of that cursor, and so the values listed here are the middle. So the range of values that you can actually get the crosshair over. You can see it's not at all centered on the trash area, so that actually confirms what we already knew in the Math Blaster community, which is that rebounds in the lower right of the screen are a lot faster and easier to hit. But up in the upper left, there's a lot of room for the piece of trash to be where it can't actually be shot. So you can imagine some of the really bad angles where it's up in that area and then bounces straight across. It can just cut across the upper left corner, but not actually be possible to be shot the entire time. So that's sort of the least desirable path if you're trying to speedrun this game. And then it's the bounce or clear detection, because it's the same place that's used for detecting whether it should bounce or whether it should just clear that piece of trash. So when it hits that barrier and the level is still going on, you haven't shot 10 pieces of trash yet, then it'll bounce it back into the border of the trash area. But if you've already shot 10 pieces of trash and the correct math equation has stopped blinking, and then it hits that detection barrier, that's when the piece of trash is removed. And then when all of the pieces of trash have been removed, that's when the stage complete comes up to the screen and you can move on with the game. So that's also kind of what explains just the clear time of like 5 to 15 seconds at the end of a trash level where the pieces need to clear the screen. I mean, there's a delay between when the last piece of trash actually is not visible on the screen anymore and when stage complete actually comes up, and that's due to this clear detection barrier where it has to not only go off screen but also up to the detection barrier. And then there's another, I think, like 3 frames, and then it pops up stage complete.